Please imagine a ball rolling. The time also, starting at time 0 would be boring. Let us start from time equals 2. You can think of this unit as seconds. Now let us consider this ball moving with a constant velocity. I just used the word velocity, but I will give a rigorous definition of this later. Let me represent this velocity with the letter v. This letter v contains a specific number, and when this is constant, such motion is called uniform linear motion. Yes, is that clear? So in this uniform linear motion, as the ball rolls along, let us say that at time 5, its coordinate reaches +7. Is that clear? Yes, this x equals +1, x equals +7. These plus signs can of course be omitted. However, in this lesson, to emphasize direction, I will write them as appropriate. In other words, this means the object started its motion from a position to the right of the origin. And now the object has arrived at a point that is 7 units away to the right of the origin. That is what this means. Is that clear? Now, although this may seem like a simple phenomenon, let us first discuss various quantities related to it. First, let us look at this change in coordinates, where the ball moved from x equals 1 to x equals 7. This is called displacement. If you are taking notes from this video, please leave some space in this section. Now then, displacement is defined as the later coordinate minus the earlier coordinate in time. In this case, it would be +7 minus +1. When we calculate this, it becomes +6. Yes, this is the displacement of the ball in this phenomenon. Normally, this quantity called displacement, including the plus sign, is typically represented by the symbol delta x. Many people beginning to study physics feel intimidated by this delta symbol. However, this delta symbol simply means change. That is, change is the final quantity minus the initial quantity. In physics, delta, meaning change, is the later quantity in time minus the earlier quantity in time. This is the definition. So the coordinate changed from x equals +1 to x equals +7. If we were to write this displacement of +6 here, delta x is +6. We can write it in the diagram like this. Is that understood? Now, this term displacement contains two very important pieces of information. First is this plus, which means rightward. Yes, this rightward direction is expressed by this plus sign. And the distance, how far it moved, is represented by the 6. Yes, this is how it works. In other words, displacement is a quantity that expresses both direction and distance traveled in one package. So please do not forget that displacement always comes with a sign indicating directional information. Is that understood? Now let us define velocity in this uniform linear motion. Velocity is a quantity that represents how far and in which direction an object moves per second. Now, as the time changes from time 2 to time 5, the elapsed time. Yes, this time interval can be written as 5 minus 2. Let us add the unit here. It is seconds. And during this time, how far and in which direction it moved is precisely the displacement we just studied. Let us add the unit meters. This is how it becomes. Yes, then this can be written as +6/3, which simply gives us +2. Yes, let us write its unit too. Meters per second, this is the unit of velocity. So velocity is defined as a quantity that represents how far and in which direction an object moves per second. While you probably use this term commonly in daily life and need not worry too much, velocity is actually completely different from speed. They are entirely different. In physics, we must be clearly aware of this difference. What you normally call speed corresponds to this +2 in terms of velocity. Yes, this 2 represents the quantity called speed, which is the part without the sign. This is like the distance of 6 in our earlier displacement example. This also does not include direction. In other words, distance and speed are quantities that do not contain directional information. Conversely, distance and speed are incomplete as information. The direction in which the object moved is not included in this information at all. Yes, that is why in velocity we properly include the rightward direction as plus. Yes, the rightward information is properly included. Is that clear? Yes, this plus represents right. Therefore, it moved a distance of 2 per second to the right. This is what we collectively call velocity. Is that clear? Now actually we can write this velocity more elegantly and simply using delta, the symbol for change that we studied earlier. This plus 7 minus plus 1, when we express it using delta, since it represents displacement, we can write it as delta x. And this 5 minus 2 represents the time interval. The change in time is what we call the time interval. Using delta, we can write this as delta t. The final result was plus 6 over 3, where 3 is delta t, and plus 6 is delta x, the displacement. Yes, so we can write this part using delta t and delta x like this. This actually becomes the general definition of velocity in physics. V equals delta x over delta t. Is that clear? This is how velocity is defined. This equation will be used everywhere as we progress in our studies, so please make sure not to forget it. Is that understood? Yes. Well, we have worked with a very simple example, but I would like to give you a few more examples. Now let us look at another example. Earlier, we looked at a very straightforward motion in the positive direction, moving to the right. Now let us look at another example. Earlier, we looked at a very straightforward motion in the positive direction, moving to the right. Let us set the origin here, and suppose that initially the ball is at coordinate plus 8. Let us set that time as t equals 2. Good, right? From this state, the ball undergoes uniform linear motion. However, let us say it moves uniformly to the left. Of course, this v is constant now, right? So from this state, as the ball rolls to the left, let us say it reaches x-coordinate plus 2 at time t equals 5. Yes, let us consider the displacement and velocity in this case. First, regarding displacement, since it is moving to the left, we can predict that the displacement will be negative. Yes, let us calculate it. Displacement, delta x, is found by subtracting the initial coordinate from the final coordinate. Therefore, this becomes plus 2 minus plus 8, which equals minus 6. If the unit of the x-axis is meters, this would be 6 meters. Yes, 6 meters is the distance. And the minus sign indicates movement to the left. Is that clear? Please note that directional information is clearly included. And for the elapsed time, yes, it is 5 minus 2, so it becomes 3 seconds. Good, right? Now we can calculate the velocity from these two pieces of information. Yes, so this becomes minus 6 over 3, which we can see is minus 2 meters per second. Indeed, the important thing here is this minus sign. It indicates the direction toward the left. Yes, and this 2 represents how fast it moved in the leftward direction. Yes, this is what it indicates. Is that understood? So when motion is in the negative direction, the sign becomes minus like this. Well, that makes sense, right? This is how it works out. Is that clear? Now then, let us look at one more example. This time, let us consider a phenomenon where a ball is moving on a horizontal floor. Again, we will set the rightward direction as the positive x-axis direction. And let us denote the leftward direction accordingly. Taking the origin here from a different position, not at the origin, at time t equals 2. Yes, let us say the ball has an initial velocity of 3 in the rightward direction. Now, this ball did not maintain its initial velocity of plus 3, but rather, let us say its velocity kept changing continuously. In this case, let us say the velocity kept increasing in the rightward direction. Yes, I have written A with this red arrow, which represents a quantity called acceleration. While we will define this properly later, for now, please think of it loosely as a quantity that represents how much the velocity changes per second. Is that clear? Well then, naturally this v keeps increasing from plus 3, and when time t becomes 4, the velocity, for example, we should draw the arrow longer here. Let us say it becomes plus 7. Good, right? Motion where velocity changes at a constant rate like this. This kind of linear motion is called uniformly accelerated linear motion. Good, right? The important thing is that in this uniformly accelerated linear motion, the acceleration remains constant, right? Now, let us think more deeply about this quantity called acceleration that we discussed earlier. Yes, we will consider acceleration in a precise manner. Acceleration is how much the velocity changes per second. We can see that the elapsed time is between 4 seconds and 2 seconds, that is 4 minus 2 equals 2 seconds. Yes, let me write down the units. During this time, the final velocity was plus 7 meters per second, and the initial velocity was plus 3 meters per second, so it becomes plus minus plus 3. This shows us how much the velocity changed. So this becomes plus 4 divided by 2, and when we calculate it, the result becomes plus 2. Yes, and this actually becomes the acceleration in this case. The unit is meters per second, and we write it with this notation. Yes, in other words, the quantity we wrote as A earlier has a value of plus 2. Is that clear? Yes, and please pay attention to this plus sign. This plus sign means movement to the right. Yes, the sign clearly tells us in which direction the acceleration occurred. And this too is called the magnitude of acceleration. In physics, when we use the term magnitude, it means a quantity that does not include the directional sign information. Yes, so this part 2 is simply 2 as the magnitude of acceleration. Is that understood? Yes, so in this case, with an acceleration of plus 2, the velocity increases by 2 each second toward the right. Now we can actually derive a defining equation for this acceleration. Please focus on this plus 4 divided by 2. So here, yes, this is this part. Yes, we can write this change as delta t. It is the later time minus the earlier time. And here, since it is the change in velocity, the later quantity minus the earlier quantity, we can write it as delta v. Therefore, acceleration can be written as delta v divided by delta t. This is the general definition equation for acceleration in physics. Yes, is that clear? Yes, this is how it works out. That is good. Yes, so up to this point we have understood what acceleration is. Now, by the way, in this uniformly accelerated linear motion, how can we determine the distance traveled? We cannot simply say that the distance is 6 meters by multiplying the initial velocity of plus 3 by the elapsed time of 2 seconds, can we? Because the velocity keeps increasing, naturally we cannot calculate the distance using the initial velocity, which is the smallest velocity. And likewise, it would also be incorrect to say that it moved 14 meters by multiplying the final velocity of plus 7 by the elapsed time of 2 seconds. This plus 7 was only at the final moment, and it did not move at this high velocity throughout the entire time. So how should we calculate the distance in this uniformly accelerated linear motion? Actually, there was someone who thought about this carefully, and that was Isaac Newton. The approach we are going to take is actually connected to the concepts of calculus. Is that all right? First, let us return to our earlier discussion of uniform linear motion.